Good morning, class. Today we are shifting to the point twos in chapter 9, and the title is What if the inequality has two variables? So we're going to look at um, things in the Cartesian coordinate plane, y equals something with x, but there will be inequalities. Before we get into that, though, I think it's important that we just take a pause and kind of review where we've been so far. So, kind of in my mind, here's a summary of some of the bigger ideas that are happening so far in this chapter. And you probably want to make sure you have something that's equivalent to this in your notes, but more importantly, that you understand what I'm talking about. So the first thing that I have over here is if I have the absolute value of some expression, and I have to be really clear, I've simplified it and I've got it down to reduce to a part where the absolute value is less than a. The absolute value is less than a value. Now, I am, for convenience, writing the absolute value on the left-hand side. The important thing is not the direction of this inequality. It's the relationship between the absolute value and the value of a, right? So I'm saying if the absolute value is less than something, and just to be clear, I could write this way here. If you look, this is exactly the same. Although my pen is dying on me here. Let me get some more ink. So it's not the direction of the inequality, it's the relationship between the two quantities. So this expression, a is less than the absolute value of some expression, is equivalent to the absolute value of some expression is less than a. So what I'm saying is the smaller thing is the absolute value. So the absolute value is less than a, and you can also have the absolute value is less than or equal to a. When I see either one of these, when I see that the absolute value is the smaller part, I know that this is going to become two separate inequalities, two parts that will be joined by and. Less than will be and. Less than, and. Less than, and. Less than, and. Over here, if I have the absolute value of some expression is greater than a, or it's greater than or equal to a, right? If it's greater, or equal to, greater, it will be two parts that are joined by or. Greater, or. So that's one idea, right? We're going to be breaking these up into two separate cases, and we have to consider two different locations. They're either going to be joined by and, or they're going to be joined by or. The other thing is that if we have an open or a closed interval, and this just means are the endpoints included or not. If I'm looking this on a number line, like an open interval would look something like this, an open interval, right? Open, meaning that those endpoints are not included as solutions. If I've got greater than or equal to, less than or equal to, these will be closed intervals, which means that the endpoints are indeed included. So with this in mind, right, and this in your notes, let's look at four or three quick examples to kind of summarize what we've been trying to deal with for the last couple of days. Okay, so for this first example that I want us to think about, I have here the absolute value of an expression. The expression is x plus 2. The absolute value of that expression is less than 7. Because this is less than, right, I'm going to get two expressions that are joined by and. Less than or joined by and. On one side, I'm just going to write this exactly as it is. I'm going to write this x plus 2. I'm going to write less than, and I'm going to write 7. So visually, when I look at it, the only difference between what I had and what I wrote down is that the absolute value symbols are gone on this side. On the other side, right, I'm just going to write the x plus 2. I'm going to flip the direction of my inequality, and I'm going to write the opposite of the 7. So on this side, it's always going to be keep this the same, flip the direction, and then opposite. Keep, flip, opposite. Now, this is all related to our lecture from 2 days ago with the guy in his house and his bicycle and his friends. That kind of provided the justification for why this is. At this point, I want to move away from that really solid understanding about why and just get into some more mechanics. So this is correct. It's less than, it's two expressions joined by and. One of them is going to look exactly visually like the expression I had, or the inequality I had. The other one is just going to be flipped and then opposite. Now I just process each of these separately. On this one, I'm going to subtract 2 from both sides, so I get that x is less than the number 7. X is less than 7. And over here, x's are greater than negative 9. So because it's an and, I can always write this as a compound inequality. I can write it as one inequality together. And if I look at it, here's the x's in the middle. The x's are smaller than the 7's, right? X's are smaller than 7's, but the x's are also greater than negative 9. And I can see that from the 2 points up here. If I want to graph this visually, here is the number 7. It is an open interval. Somewhere over here is 0, and then somewhere over here is negative 9. On both of these, they're open intervals. And my x values are those things that are in between these two spots. So all of the things here are x's. Let's look at another example. So on this one, I have greater, right? I have the absolute value of 3x plus 7 is greater than 12. Because of this greater, let me make this a little bit thinner. I'm going to be joining these two parts with the word or. Over on this side, everything's going to stay visually in the same order, same direction. So I'll write the 3x plus 7 is greater than 12. Or on the other side of this, we've got it. I'm going to keep this the same, 3x plus 7. I'm going to flip the direction, and then I'll take the opposite. Keep the same, flip, opposite. Same. All right. Now for each of these, I'm going to take away 7 first. So I've got 3x is greater than, let's see, 12 minus 7, 7, 8, 9, 10, 11, 12 is 5. Oh, Mr. Roberts. And then I'll divide both sides by 3. So that gives me that x is greater than 5/3. Or over here on the other side of this, I'm going to add, take away 7 again. When I subtract 7 this time, because I had a negative 12, 7, 8, 9, this becomes negative 19. Okay, and I'm going to divide both sides by 3 now so that x's are less than negative 19/3. So this is the word or. Or statements I can't join into one because they're pointing in opposite directions, right? It's or. It's over here, or it's to the left, or it's to the right. So on my number line, here's roughly the number 0. Then I have this positive 5/3, and I do have an open interval again, 5/3. And then over here I have this negative 19/3 and again an open interval because it was strictly greater than in the original problem. And my solutions are those things that are to above this direction, or they're this direction. They're over to the right, or they're over to the left. So these mechanics seem to be working well for us. I guess a good thing to do would be to look at a verification of that. So let's take a quick look at GeoGebra here. So in GeoGebra, I am going to type that expression as 3x plus 7, and I'm going to make that greater than 12. Whoops, not question mark 12, greater than 12. And when I do that, you can see I end up with the two spots here, right? One of them, if I look at this spot, this is my positive 5/3, which is what, 1 plus 2/3, 1 and 2/3. You'll notice it's a dashed line. That's why we have an open interval. This line is not included here. Over here, this point is not included. This is negative 19/3. If I want to confirm that those are really the points, I could just type negative 19. I could say x is equal to negative 19/3, and I can see, yeah, that's definitely the 19/3. And then I can also look at the x is equal to 5/3. Yeah, and that's the x is 5/3. Great. So we have a pretty good visual confirmation that things seem to be working as they are supposed to. Let's look at a third example here. All right, so for this one, everything I've talked about assumes that we have the absolute value isolated. I don't have the absolute value isolated here. So before I proceed, I want to get the absolute value alone. And for me, preferably, it's on the left-hand side. So I'm going to begin by adding 5 to each side of this. So this is going to become 2 times the absolute value of 5x plus 4 is going to be less than the number 30. If I have unequal things and I add the same thing to both sides, that inequality, the direction and everything still stays the same. So this is exactly the same. Now I'll divide both sides by 2. So the absolute value of 5x plus 4 is less than 15. If you have an inequality and you divide both sides by a positive value, you still preserve that inequality direction. So now this is less than. So these things are going to be joined by and. We will be having open intervals for this. And again, I'm just going to write this exactly as it appeared, 5x plus 4 less than 15. And on the other side, I'm going to write the 5x plus 4. It's going to be greater than negative 15. So it flipped direction. Keep the same, flip direction, opposite. Keep, flip, opposite, same. And then for each of these, right, we're going to subtract 4 from both sides of the inequality and divide by 5. Over here, that looks like 5x is less than 11. Therefore, x is less than 11 fifths. And over here, 5x is greater than negative 19. Therefore, x is greater than negative 19 fifths. And again, these are joined by the word and. So I can write these as one super inequality together. At my x's in the middle, my x's are smaller than, not or equal to. My x's are smaller than 11 fifths, but my x's are greater than, negative 19 fifths. And then on a number line, 11 fifths, here's 0. 11 fifths is like, what is it? 2 and a fifth. 1, 2 and a fifth. So I've got an open interval at 11 fifths. And then I have a closed interval. 19 fifths is like 3 and 3 fifths. So 1, 2, 3, and a little bit more. This is negative 19 fifths. And this is also an open interval. And my x's are those things that are in between these. So any of these values of x would make that inequality true. Well, probably not enough, but we're going to stop there because we're at 12 minutes, and that's just a review. So we need to get jetting on to our new topic. I do want to point out, though, that in this fourth example that I had selected, there's something interesting about that, right? This says the absolute value of something is less than negative 12. So just say that to yourself a few times. The absolute value of something is less than a negative number. And if you think about that for a minute, you quickly come up with a solution to this problem, right? Just with reason. So think about that and maybe say right now in your room, like, oh, that means what? Okay, just say that. But the absolute value of something is less than a negative number. All right, we're going to try and finish up with some thought experiments here in GeoGebra. We'll spend probably the rest of our time here. So let's begin by considering not an inequality, but let's consider an equation that has two variables. So let me type in here y is equal to negative 2x and plus 3. Y is equal to negative 2x plus 3. So first question I have is, when I'm looking at this, right, there are a lot of things that are solutions to this. The first point I want to ask about is the point negative 1, x is negative 1, y is 5. Is that point negative 1, 5 a solution? And we can see that quickly in GeoGebra when I look at negative 1 comma 5. It's like, yeah, I'm right here, right? That point lives on this line. If I was to put negative 1 into the equation, negative 2 times negative 1 would give me positive 2, and 2 plus 5 is 3. Absolutely, when x is negative 1, y becomes 5. So because that's true, because 1, 5 makes this equation true, I know that 1, 5 is the solution to this equation. What about the point 2, negative 1? So if I look at the point x is 2, y is negative 1, you can see, oh, look right here, similar thing happening, right? Similar thing happening. And if I looked at the point x is 2, comma, y is negative 1, I can see, well, that's a solution also, right? because it is on this line, it makes my original equation true. So basically what we're saying here is that if a point, right, lies on the line, right, if a point is on this line, it has to make this equation true. And points that are not on the line don't make this equation true. So yes, there's an infinite number of points that make it true, but man, there's a lot of points that don't make it true, and I could just pick them all over the place. All right, so what makes this true is points that live on the line, the object that we're talking about. So what I would like to do if you were in classroom is I would give you and probably a group of the people that you're sitting next to a good chunk of these points. These are different points, and the thing is that some of these points will make the inequality that I've written down in red true, and some of them will not. So for example, if I look at the first point when x is negative 6 and when x is negative 1 and y is 6, if I place a negative 1 into here, this becomes negative 2 times a negative 1 plus 3, which looks like, let's say negative 2 times a, which looks like 2 plus 3, which looks like 5. Well, is it true that 6 is greater than or equal to 5? And the answer is, yeah, it is true that 6 is larger than or equal to 5. So this point is a point that I want to remember because this point makes this inequality true. Let's go over here. Let's look at 3, 3. If I put 3 in for x and 3 in for y, both, right, y and x, this becomes negative 2 times 3 is negative 6, and negative 6 plus 3 would be a negative 3. So what about this? Is 3 greater than or equal to negative 3? Really? 3 is greater than negative 3, right? So this point is a point that I want to consider as true also. So I'm jumping around now. I'm picking ones that worked. I wonder if I pick this one, if it would work. Let me put this in. So if I put this point in, here's my y, here's my x. If I put in x is 2, this is going to become negative 2 times negative 2, which is negative 4. And negative 4, 2 times it is negative 4. Negative 4 plus 3 would be negative 1. And it is true that 4 is greater than or equal to 1. That is always true. 4 is greater. So this is a point that I want to make sure I'm keeping track of. I can't find any that don't work. Let's not skip. Let's do this one next. What about this one? If I plug this in, here's my x, here's my y. I've got a negative 2 times a negative 2, which is 4, plus 3. So this is 4 plus 3, which is the number 7. And then here I've got y is 2. Is 2 greater than or equal to 7? Is 2 greater than or equal to... No. 2 is not greater... Okay, so this is my first one. This one does not work. It does not work. Let's see if I can... Maybe I can see a pattern. Let's see. I think this one would work. Yeah, I think that one would work. What about this one? I think this one won't work. Negative 2 times negative 3 is 6. 6 plus 3 is 9. And then over here I have 4. Is 4 greater than or equal to 9? No, that does not work. Now, what's nice is when we get a bunch of students to start looking at all of these points and we start plotting all these points, we start to see a pattern. Let's jump to GeoGebra. So if I type in the points that worked so far, a working point was -1, 6. That was a good point that worked. Another working point was 2, 4. That point worked. 2, 4 worked. That was nice. Another point that worked was 3, 3. Oh, no, not 3.3. You need to go away. It was 3, 3. That was another point that worked. X was 3, Y is 3. That worked. A point that did not work was this point. -2, 2 did not work. Did not work. And then another one that did not work was -3, 4. That point negative 3 comma 4 did not work. Oh, so far with only 5 points up here, these 3 worked and these 2 did not. So hopefully we can see what's going on here. This inequality says that my y values have to be greater than a boundary, right? My y values have to be greater than or equal to the boundary. Well, what does that look like? Oh, where did you just go? Let me delete this and type that again. My y values, y's have to be greater than or equal to the boundary, and the boundary was negative 2x plus 3. And when I look at it, you can see, oh, look at that. They can be the boundary because this is a solid line, right? So all the points on the line are included, and we talked about points that were on the line earlier, but also the points that are greater than the line also worked. So this is the idea if we're solving an inequality like this. Now, it's incredibly inefficient to list all the points, right? In fact, you could never have a list big enough to include all the points that would work as a solution. So we don't draw out massive lists like this. What we do is we just recognize that some of our points are solutions, some are not. In this case, all of the points that are greater than, they're above the curve or equal to the curve, the way this is written, are solutions. So everything up here would work, and everything down here does not work. So my solution does not include those 2 points, but it definitely includes these. And it also includes a point like negative 1, 5, right? We talked about that earlier, negative 1, 5. That is a solution for this one because the boundary is included. It says greater than or equal to. Now, if we were to change the or equal to and just make it greater than, all of a sudden when I do that, you can see this becomes a dashed line. So when we show that the boundary is not included, right? So if we're asked to solve an inequality like this, what we're going to do, our strategy will be to graph the boundary. So graph the boundary. If it is strictly greater than or less than, the boundary will be a dashed line. If it includes the or equal to, right, the boundary would be a solid line. And then we just test a point on either side, and just testing one point should give me, if I don't make an error, and you know that I'm prone to make errors, but if I tested a point either above or below the line and I could see which side the points were working, I would know which side to shade. So for example, if I put 0, 0, again, one of my favorite points to test too, the number 0 was a favorite point to test earlier, but if I put 0, 0 in here, I get 0 is greater than or equal to the number 3, right? Because this becomes 0 and this has become 0. Well, 0 is not greater than, 0 is not equal to the number 3. So I know that the points down below here do not work. Therefore, the points above are the ones that do work. So we're going to leave it there right now. We're at about 23 minutes, and given some of my recent talks, that's enough. So we'll stop now, and I hope that these are solid initial ideas about how we deal with absolute value. Not absolute value, inequalities that involve 2 variables, in this case, x and y. This is Mr. Roberts. Thanks for being here. Nice seeing you. Did I see you? No? Nice knowing that you're here, and I'll see you in class again soon.